Computational Intelligence Society webinar, Neuro Combinatorial Optimization for Routing. We are delighted to have you with us. I'd like to begin by thanking Ying, the chair of the CIS webinar committee, for her leadership in organizing this session, and to express our appreciation to Ya-Hui for sharing their expertise with the community today. Before we get started, I just note a few housekeeping items. Lines will be muted throughout the presentation to ensure clear audio. You may enter questions in the chat box at any time, and we'll reserve time at the end for Q&A. This webinar is being recorded and will be posted on the CIS website at cis.ieee.org. We also invite you to stay connected with the Society and learn about future events by following us on Facebook, LinkedIn, and Twitter. I will now turn it over to Ying to introduce our speaker.
Thanks, Tom. Hello, everyone. Today, we are pleased to invite the Associate Professor Ya-Hui to give a talk on neural combinatorial optimization for routing. Firstly, please allow me to introduce Ya-Hui Jia. He's an associate professor at the School of Future Technology, South China University of Technology. He's the chair of the IEEE CIS Task Force on Evolutionary Scheduling and Combinatorial Optimization, and a committee member of the CCF Technical Committee on Cooperative Computing. He previously served as a postdoc research fellow at the Victoria University of Wellington in New Zealand. His main research interests focus on intelligent optimization algorithms, including evolutionary computation and deep reinforcement learning, as well as the applications in combinatorial optimization problems, intelligent transportation, and smart energy. He has published more than 50 papers in leading journals and conferences, including IEEE Transaction on Evolution Computation, IEEE Transactions on Cybernetics, and IEEE Transaction on Neural Networks and Learning Systems. She serves as an associate editor of Journal of Renewable and Sustainable Energy. Now, please join me to welcome Professor Ya-Hui Jia.
Thanks, Ying. And so I will start to talk about some of my works about neural combinatorial optimization for routing. I'm Ya-Hui Jia, and in English order, Ya-Hui in Chinese order, and from South China University of Technology. And this webinar is provided to you by IEEE CIS. And let's go. So here's the catalog of my presentation. And first, I will talk about some background, and then I will show some of my works in three aspects: in generalization, in arc routing, and in dynamic. Finally, I will give a conclusion. First of all, we need to define what is the routing problem. So the routing problems, basically all the routing problems originate from the traveling salesman problem, TSP, and given more and more constraints, it becomes the other problems like TSPB with backhauling, and with time window we have TSP-TW, and we have if we have multiple vehicles, we have MTSP, and if we give some the vehicle some capacity constraints, it becomes CVRP like that. And all the routing problems, most routing problems, the objective is to find the shortest path to finish all the tasks. Maybe not the shortest path, but sometimes it's minimal cost to finish all the tasks. But most of the time, it's the shortest path. Here in the left, I show a picture of using the greedy algorithm nearest first to build a solution of a TSP problem with I think there's 10 tasks in the on the map. Okay, so for routing problems, it's a very traditional combinatorial optimization problem. So usually we use optimization method to solve it. So For the optimization method, usually we give given a problem instance, we design evolutionary optimization algorithm, maybe other algorithms, and we get the solution. Okay, so what you need to do is to design the algorithm operators or the components. You can also use some other algorithms instead of evolutionary optimization algorithms. Okay. Another way to solve a problem is currently we call it learning to optimize. And what is learning to optimize? First, we need to use a lot of many problem instances to train a model. Usually, it's a deep model and trained by deep reinforcement learning algorithms. Sometimes it's by supervised learning methods. And after that, we get a model this model can be a solver and to solve the new problems, to solve the unseen problems. So if we got the model, we got a new problem instance, we can get the solution of this new problem instance. So for L2O, and usually what you need to do is choose the choose the appropriate reinforcement learning algorithm and design the neural network for the model. Okay, so neural combinatorial optimization usually belongs to the second category. It belongs to the learning to optimize, and for the traditional evolutionary algorithms, it belongs to the left part. Okay. So here is a map of how the NCO methods can be categorized. Okay. We have these three different NCO methods. The first is called construction methods. What it means that we build a model, the model construct the solution step by step. And the second is called improvement method. And the improvement method is meaning that you get a solution in the first place, and using the neural network, using the model to guide to select appropriate operators working on the solution, to refine it over and over and again, and to improve it. And the last one is called prediction using diffusion model and LLM. It's not I'm not very familiar with this category, so I won't. You can find some other papers to about it. So today my research is mainly about construction methods and two commonly used model architecture is graph neural network and transformer. So how to use a transformer to get a transformer model to solve routing problems, and the inputs is the features of the problem and the candidates, and just like the greedy algorithm, you choose from one task and you decide to where to go and to go the next task, and for greedy algorithm you always choose the nearest one, but the model will give you a score to help you to judge which one should you go and in the next step. And the model is trained by reinforcement learning algorithm. And about the basic idea about the reinforcement learning, I won't talk too much here. I think all you guys should already know that. And the agent here in the right figure, and the agent here means the model, and the environment means a lot of problem instances. And we give an action means that we solve these instances, and the reward is just the objective values we obtained. Okay. The input is still the features of the problem and the candidates, and the output is are usually the probabilities of the candidates for routing or for scheduling problems. So here we talk about routing is the probabilities of choosing the next task. So if you are familiar with optimization algorithms, you may know that if we check the precision optimality, we know that the heuristic is worse than meta-heuristic, and the meta-heuristic is worse than exact algorithms. This is not 100% correct, but maybe 90% correct. Okay. If we check the efficiency of the speed, execution speed of these algorithms, and it's reverse, and the heuristic algorithms usually is the most efficient, the fastest one, and the heuristic, meta-heuristic is in the middle, and the exact algorithms are usually computationally very computationally expensive. So where is NCO? And if I put NCO, it will be here, just between the heuristic and the meta-heuristic. It has the heuristic speed, and sometimes it's slower than some simple heuristics, but sometimes it's much faster than very complex heuristic like RKH, like that. And the performance, the effectiveness, the precision, usually the model, the performance of the model is worse than the meta-heuristic, but better than some simple heuristics. Okay, so for neural combinatorial optimization problem, currently we are working on 3 aspects of the the first aspect is about model generalization. For the current models, if we trained on a 100 scale problem, like a 100 scale KSP problem, and usually it can solve 100 that kind of scale unseen problems very fast and give a very good results, even optimal results, I think. So, but its problem is that with that model, if you try to solve some other scales, bigger scales, or some problems with other distributions, maybe you trained with the normal distribution on the map, and if you want to solve a clustered distribution problem on the map, it's the performance of the model is usually not that satisfactory. And another one is currently with the LLM, with the LLM is very popular, and it can basically solve anything. It has a lot of different knowledge, and for people we doing combinatorial optimization research, we think that can we build a model that can solve different variants of the routing problems. This is the first part, and for the second part, we have other different combinatorial optimization problems, other complex routing problems like the arc routing problems, like robots routing problems. And for these different problems, we really care about the feature representation and how to extract effective features about these new problems. And the third aspect is about information observation. It means that for the static problems, usually we know all the information beforehand and in advance. But in dynamic and stochastic scenarios, in real-world applications, sometimes your information is not correct. Sometimes you don't know all the information. You just know a part of the information. So these are 3 aspects we are currently working on. And so for the next part, I will talk about the generalization, how to improve the generalization of a model, of an NCO model. So why generalization? Why do we need generalization? So first of all, training on large-scale instances are insanely expensive. If somebody have already tried that, you may know that. And so currently we can, for me, I have two very powerful CPUs, but 5090 like that, and I can only train a model to solve with maybe VRP for VRP problem maybe 1000 tasks, and the scale is just like that. And if the scale is larger and the CPU the GPU cannot support it, okay. And also, there are many different distributions, normal distribution, cluster distribution, and maybe for arc routing, we have small world like that, and different distributions. And also, we have many different VRP variants, VRP TW, open VRP, and some other VRP with pickup and delivery, and like that. Can we use a single model to solve them all? And these are problems. The issues that we need to solve. Okay, first we talk about the scale generalization ability of the NCO. Actually, for scale generalization, in essence is quite similar to the distribution generalization. So I will talk these two scenarios in one work. Okay. One of the bottleneck of NCO is its generalization ability to large-scale problems and problems with different distributions. And for this bottleneck, many people have come up many different ideas. The first kind of idea is to use the expert knowledge to improve the neural network, to design some special neural networks. So basically, it's about a transformer, but you can design some different modules in that transformer architecture, and thus to improve the generalization ability of the model. And then after you refine, you improve the neural solver, the transformer itself, and somebody said that maybe I can train using the data, using my expert knowledge to train another smaller network to help the main solver, and in the decoder part. So they have the second way to improve the NCO model, the generalization ability of the NCO model. But when I read these papers, I found a very interesting problem, Why didn't they compare their methods with greedy? I checked all the papers, and I think it's 2 years ago, I checked all the papers, and I found that after they designed their methods, designed their model, they never compared their model with the greedy methods. So I did an experiment. I found that for the model trained on maybe 100 or 200 scale, and when the model is applied to 10K model or like that, and the performance of this model, they claim that they have very good generalization ability, but their generalization ability is even worse than the greedy algorithm. So that's the problem, right? And you feel that is wrong. That is wrong. We can, if a model, the generalization ability of a model is even worse than greedy, how can you claim that it has a strong generalization ability? I found that greedy is even better than some NCO methods in terms of generalization ability. Okay, and why then? I'm wondering, why are they worse than greedy? I checked the reason. I found that the reason, when the size of the problem increases, maybe also the density changes, like the distribution changes, there will be a attention dispersion phenomenon. Okay, and I call it attention dispersion. We trained a model on 100 uniformly distributed tasks, and we found that when we use it to solve the 100 clustered distribution task, the high score points, there are more high score points, and when we test on the 1000 uniformly distributed tasks and distribution task, we found that it has more and more high score points. And when you make a decision, you know that if I give you a bread, you eat the bread. If I give you a bread and an egg and some milk and maybe some other food, and it will be harder for you to choose. Okay. So what's the reason of this attention dispersion? We found that's mainly about two reasons. The first is the neighbor nodes. If we train on a 20 scale problem and we test only 100 scale problem, we found that sorry. We found some neighbor nodes of these two green nodes and the yellow nodes. Okay, nodes are the neighbor nodes. They have a high score, and we have also found some we call the random high score nodes, the purple nodes here. It is far away from the two green nodes, but they still get very high score. And also we theoretically proved that attention dispersion is inevitable if we train our model on small scale instances and test it on the larger scale instances. This attention dispersion is inevitable. Okay. We want to solve this problem, right? And how to solve the attention dispersion problem? And we come up with a very simple idea. Since all the methods before our work are worse than greedy methods, then we think that we can just use greedy to help our neural solver. So we didn't change anything about the neural solver itself. We didn't add any new neural network. We didn't add any new parameters here. We just use the distance between two nodes and to reshape the attention. So for here we can see A bar equals A and plus B, and the A is the original attention score, and the A bar is the reshaped attention score. The B is what we have designed. So we designed that B is equal to the negative log and distance between the S node and the this nodes. And you can just ignore the negative dij. This the second one is just for the to make the algorithm more efficient. But if we use only the negative log dij, that is also enough. It's already enough. So we add this after we get the attention score. After the decoder, we have attention score, and after at that time we add a bias, a B here, to reshape the attention. We got A bar, and finally we use the A bar after a softmax function to decide which node should we choose. We have a proposition that this method we call DAR, and DAR can reduce the entropy of the probability distribution, mitigates the phenomena of the dispersion of attention score. And we have designed a way to verify it. And the idea is very simple, that we choose the first half of the probability, and we add some on them and choose the another parts, the later parts, to decrease their probability to be chosen. The far away, the second part represents the nodes that are far away from the current node. Okay, and we only need to verify that the entropy of the first one, of the original one, is larger than the entropy of the later one. And after the modification, we may know that the phenomenon, the attention dispersion phenomenon is mitigated. Okay. And so for the why do we choose using the negative log d? And since the reason is quite simple, because we use usually we use the softmax function to calculate the probability. So only the negative log d is effective. So if we choose fd equals 1 divided by d like that, it would disable the neural solver, degrades the algorithm to greedy if the scale of the problem increases. We have proven that. And if we use the fd equals minus d negative d, it would disable the greedy and when n goes to infinite. So only when we use fd equals negative log d, and it is effective when no matter what's the scale, okay? So after that, we have done some experiments. We found that over DAR, the last column, and we found that it's better than the ERG and the GLOP and the original POMO, and also it's better than the greedy algorithm. And to see the attention score, we found that for DAR, the attention score is really reshaped, and the number of the high score nodes is much smaller than the fewer than the ERG methods and the POMO methods. And also we have tested our thoughts, our idea on some other problems like VRP-TW and capacitated arc routing problem, and also on the knapsack problem. We found that this idea works for all other kinds of COP as well. Okay. And after that, we have considered the generalization ability of NCO on different variants. And people may know that the MOE architecture, and some researchers have used the MOE architecture in the neural model, and to try to make the model capable of solving many different variants. But we found that the original MOE structure is not that good, since it divides different problems very separately. We can see from the figures that different color means different problem. Actually, we think that different problem, they have some they are not totally different. They have some similarities. They have something in common. So the reason is that we have checked results, optimal results of some variants, and on the same distribution. You can find that the node is the same, but the problems are different. For the first one is the CVRP, and for the last one is OVRP-TW. And for some of the solutions, the optimal solutions, we might find that they have a lot of routes in common. So we think that these problems, they have something in common, they have something different. So we think that we shouldn't use the MOE on the feed-forward layer. Instead of that, we should use the MOE structure in the multi-head attention layer here. We use a gate to choose which attention to use. Here, another reason is why we do that instead of moving this gate to the feed-forward layer as the normal MOE, is that for different problems, we think that they have different features, right? They are essentially are different in terms of the constraints. For instance, if we think about the CVRP, we know that for every node, it has its coordinates and it has its demand, right? But for VRP-TW, every task has its coordinates, have its demand. Also, every task has its time window. So if we use a single model to solve different problems, we need to map all the different problems in the same decision space, in the same feature space. But if we map a three-dimensional feature into a maybe 128 dimensional space, and it's totally different from mapping three-dimensional features, three-dimensional features into a 128 dimensional space. And if you consider to take the time window, if you think the CVRP may be a special case of VRP TW, and you set set the time window as 2.0 for the VRP case, so for the CVRP case, and I don't think that is very proper to do that, although it's a common way to do that. So we have moved the gates in the multi-head attention, so that for the different attention we can use the gate to choose whether if it is a CVRP problem, maybe we just disable, we just don't choose the time window, the attention to for the time window part, okay, but it is automatic chosen. So we have moved the gate, moved the MOE from the feed forward layer to the multi-attention layer, and we have also for different variants, if we want to use a model to solve different variants, we think the traditional IR methods, that the reinforced algorithm is not enough, since the IR should consider more diverse actions instead of being too sure. If it is too sure, it means that it's already biased to a single problem instead of handling all different kinds of problems. So we have add another entropy part here, bias here, and it's quite like the soft IR, okay. And after we doing these modifications, we found that the performance is better than the previous models, and we found that from our figure, we found that some problems are quite same, maybe similar to each other. Like here is, as we see, the CVRP and the OVRP and the VRPL. These three are quite similar to each other, and VRPB itself in the bottom left corner, and if some problems with time window, VRP-TW, OVRP-TW, they are in the right up corner there. So meaning that they truly have something in common, and but some constraints can separate them, totally separate them, like the time window constraints. And we have published this paper in Transactions on Artificial Intelligence. Okay, then I will talk about something about arc routing. So what is arc routing? Arc routing is different from the vehicle routing TSP problems. The tasks are arcs instead of nodes. And there is a graph which may not be dense. For VRP, for TSP, usually we define the problems on a map that we assume that we can go from one task directly to any other tasks, right? But for arc routing problem, we got a graph that is not very dense, so it's much harder than the VRP problem. So why is arc more difficult? The first is that the task of TSP and VRP are in Euclidean space, have coordinates as features. So they have x, and y for their features, but for arc routing problems, there is no coordinates, and the problems even does not satisfy the triangle inequality, so you cannot map the problem into a Euclidean space. So there are two things we need to consider. The first one is how to extract the features. what can we do? What kind of feature we can use to represent a problem, to represent the tasks? And the second one is the perception fields. For the VRP problem, usually we use a global perception field. That means every node can see every other nodes, right? But here in arc routing, we have a graph. Can we do that as the same way as we do in the VRP? I doubt that, so I did some research. First one about feature. Graph neural networks are good tools for feature learning of arc routing problems. So if you know graph neural networks, you found that if we have a graph and you can use a graph convolutional neural network, you can use a graph attention model for feature learning. But since I did the vehicle routing problem in the first place, and I'm thinking that are there any other simple ways for feature learning? So I invented a traversal-based feature extraction methods. So if we got a weighted graph for an arc routing problem, and first we make it unweighted graph, and then we relabel the this index of the nodes from A, B, C, D to 0, 1, 2, 3, like that, and make it a numbered graph. But the number is given by some traversal methods, either depth first traversal or the width first traversal. After that, for each arc, we may have U and V represents the two verticals, and FU represents whether U is the dipole, so as FV. And we also have another feature, D, U dipole represents that's the distance from U to the dipole. And we also have a normalized cost and a normalized demand of this arc, okay? So we have these features to represent arc. And another one is about perception fields. And for arc routing problems, usually if you check the solution, you may find that the vehicles just usually execute the nearby tasks in sequence. For these simple problems, for E0 to E4 here, if we have a vehicle, we know that we can execute E0 first, and then E1, then E2, and E3, and E4. You will not use the vehicle to execute E0 in the first place, then go to E2 and back to E1, right? That's a wrong way to use the vehicle. So considering that, and we have come up with a new idea about it's called adjacent local attention. What does that mean? That means that traditional attention considers the relationship between every pair of tasks, but we only consider the adjacent local attention, meaning that only the adjacent tasks are considered for a specific task. So if the vehicle currently doing the tasks E0, we only consider E4 and E1 to pay attention to E4 and E1. Okay, that's we call adjacent local attention. And with traversal-based feature and adjacent local attention, we combine them together. We got our new method we called AEGT here. And here's the picture is the whole architecture of the model. And we have published this new model on IEEE transactions on intelligent transportation systems. And the results are quite good, and the this method means it's the best. It's a meta-heuristic algorithm, and it accepts that for the PS means the heuristic path scanning algorithm, and a different version of path scanning algorithms. And for POMO, MATNETs and POMO regrets are NCO methods. Okay, except this meta-heuristic methods, we found that our methods is better than the all the others. Also, we have tried to did some other experiment to verify the effectiveness of our feature learning methods, like we use the DFS and we use the BFS, and we found that for task dense situation, the breadth first traversal is a very good choice. It is even better than using the graph convolutional neural network. But adjacent local attention is too rigid. We have this. We have using our expert knowledge to decide. You can only pay attention to the adjacent axis, and we think that is too rigid. And we want to let the model learn which should be ignored by itself instead of we tell the model. We limit the model. So we have come up with a new idea that using two multi-head attention module here, and one module to learn which to focus, and another learn which to ignore. Okay. And also we have promote our model to a multi-dipole problem, and here's some other techniques to make the model even better, but I don't have enough time to introduce it, so I will go it very quickly. And also we come up with new augmentation methods, and finally we have combined them together to solve the multi-dipole capacity arc routing problems, and we published this paper on IEEE TCI, and the results are quite good. But on the MD-VAL benchmark, the EFAM model is better than the baseline POMO, but it's still worse than the raw cache. Raw cache is meta-heuristic algorithms. It indicates that for irregular graphs, the generalization ability of EFAM still needs to be enhanced. Okay, the results show that the edge filtering attention can delete these non-irrelevant nodes here with small possibilities. Okay, last one is about dynamic. So what is dynamic routing? Dynamic routing means that new requests appear during the travel. So after the vehicle already during the vehicle journey, and some new requests are kept being reviewed. That's the dynamic routing. So why is dynamic hard? First is partially observed information. The second is changing scale. Changing scale meaning that after maybe you in the first place you know 20 tasks, but when you're doing the tasks, doing these tasks, executing these tasks, and the new orders keeps coming, maybe the problem scale grows to 40 and 50 like that. Traditional DRL joint training of encoder and decoder and struggle. This traditional DRL struggles in dynamic environments, and we have adopted another a different way of training. It's called decoupled training. This method is not created by, it's not designed by us. It's designed by another professor in Science University. Okay. What's the meaning? That means that the encoder for the transformer architecture, encoder extracts special features from nodes, and it needs to be generic and stable. Decoders makes the routing decision. So we have an insight that different since they have different responsibilities, we joint optimization cause interference. The solution is that to split training these two separate phases, and we first teach the encoder to read the map, and then teach the decoder to adapt the dynamically. Okay, and the decoupled training architecture is here. From here, I can move on to this. For the first phase, we call the for reviews, and we have assumption that all those information are known in advance, so we didn't mask any node to the encoder, and we use a variable problem size per instance to train it. And the reward normalization by node divided by node count n. Okay. And the goal is to train a versatile encoder with an initial decoder. In the second phase, we freeze the encoder weights and train decoder only, and the nodes are reviewed progressively over time. So the goal is to let the decoder adapt to the real dynamic environment. And the model works very well, and we published on the ICRA conference, and the results shows that we are better than many different problems, even greedy and some like a robot FD, they are also NCO methods. Okay. What we are still studying is currently is that most NCO works are based on single agent IO, no matter static or dynamic. So for static problems with more than one vehicles, decisions are made route by route. So it's in essence, it is a single agent. It only considers one vehicle, and it's using uses one vehicle to mimic multiple vehicles. So for dynamic problems, currently most studies about TSP instead of VRP because they are using the single agent IO. So we are currently working on the multiple agents DIL for dynamic VRP now. We have submitted some papers, but we haven't got results. So conclusion, we give you some take-home message. The scaling law works well on NCO research field, okay? And more data and a larger model usually lead to better performance. And arc routing still needs better methods, especially for the problems that are not sparse and not dense. It's in the middle part, like maybe 20, maybe 50 or 70% of the tasks are arcs are tasks, and not all the asks are tasks. That kind of problem is very hard. And the dynamic and stochastic problem are still blue ocean. And hybrids, there's a trend to hybrids with LLM and other techniques like diffusion. I haven't worked on that, but I see many papers working on LLM already. Okay, that's all my, here's the related papers of my presentation, and that's all my contents. Thank you. If you have any questions.
Thanks, Ya-Hui, for your talk. And I think we have two questions right now in the chat. The first question is, could you also highlight the training time for results on slide 12? Slide 12.
Page 12. Page 12. Here. The time here is the solving time. It's the test. It's the solving time. It's not the training time. Here, the time means that we solve a problem. We solve this problem. How many seconds it takes. It's not training. So usually.
Okay, and I think so the next question.
Okay.
You go ahead.
For training, usually it takes maybe half day or 1 day, like that. Yeah. Okay.
Okay. The next question: how can we combine neural networks and multi-objective meta-heuristic algorithms?
You mean NCO with multi-objective, right?
Meta-heuristic algorithms.
Combine them.
Oh.
Okay, that's a good question. Since we are currently, we just submitted a paper that combine NCO with meta-heuristic. We used the idea. Since I already submitted the paper, I can share it with you. That's already. We can use meta-heuristic to solve some small scale problems, and use the solution as some using some supervised learning methods to help the reinforcement learning to make the reinforcement learning faster, and that's what we have done. And for multi-objective, I haven't done much. Yeah.
I think we have a follow-up question for the first question, so I will ask you first. How do we justify the time it takes for training the NCO or reinforcement learning model compared to exact measure like a branch and a bound?
Okay, for traditionally for the pure optimization methods like exact set branch bound and branch press like that, it's it don't usually that's these methods we don't need to train them, right? And so all the time it cost is the solving time. And for the training time, so if we compare the training type of NCO with them, I don't think that's fair, but if we don't need to consider the training time of NCO, that's also not fair either. So I haven't come up with a good way to compare these different methods. And the common way currently is just to compare the solving time. And clearly, if you use a neural network model to directly solving to construct this solution, the time is quite shorter than using a exact algorithm. That's my answer.
Okay, thanks. Let's go back to the third question. Are these slides available anywhere? Yes, we will release the slides in the IEEE CIS web page, the webinar repository, and also the recorded video. So you can find the slides and the video there. So the first question, when you train the model for generalization ability offer several VRP variants, how many datasets from each of these variants are selected?
Okay, this quite. So for these problems, we can find that they have different constraints. Like for traditional VRP, it only has the capacity constraints. For open route, it has different constraints. Then for backhaul, it has another. For time window, it has another. Right? Usually, we only consider the one constraints for each problem as the training. But when we test all the generalization ability of our model, we maybe created an O VRP TW like that. But when we train it, we just train using the basic version of this VRP, like CVRP, like VRP TW, like VRP backhaul like that. You can find how many different variants we have used in training and in testing in the paper. Okay, I didn't remember the specific number of how many variants we have used in the training.
Okay, and I think Tom also posted the link for the webinar, the archive of the webinar and the slides in the chat. If you would like to have the previous slides for the webinar and the record, you can go the link to find it. And the next question, did you use reinforce for all reinforced learning skill?
Yeah, I know that algorithm. It means the algorithm. Yes, most of the time it is reinforced. But here we use the reinforce, but the loss function we add another different part here. But still the reinforce algorithm.
Okay.
Yeah.
I think there's a request in the chat. I request you that please conduct the webinar in future, especially on meta-heuristic algorithm. Yes, we will try to invite the other speakers on this topic. Thank you. And do we have any more questions? So I would like to ask one question. I think in your slides, you mentioned the feature representation learning in your second work, working on the feature learning. So I was wondering, for different type of combinatorial optimization problems, are there any guidance for designing such kind of feature learning methods? It's based on the problems, or we can have some general solutions to different kind of.
Currently for routing problems, if you have coordinates, using the coordinates, and if you don't have it, try to map it into a Euclidean space and to use the coordinates. For other features, I think that you definitely will use it, like the cost, like the demand, like that, right? And for as if you want to use the supervised learning technique, and feature extraction is feature design are quite important and are different than currently the reinforcement learning methods. And you may find that in Xiaodong Li, the RMIT Xiaodong Li's work, and we have the current the paper we have just submitted using supervised learning to help the reinforcement learning. That work we have designed some other new features, but currently it's all about expertise, using your expertise, using your brain, using your intelligence to come up with some features instead of a universal way to design. Yeah.
And I think regarding your talk on generalization ability, I'm wondering whether you train your model on the data if your model is trained on your training data has a different distributions from your test data, or you just use the same distributed data and
we use the
testing.
Yeah, we use the different we for the generalization ability, we test it we train it on maybe like that in 100 uniformly distributed nodes, but we test it on 100 cluster distributed nodes and also on larger scales 1000 uniformly distributed nodes, like that.
So in your results, if we go to the slides of the results, which means you have trained the model once and then test on different kind of instances.
Yes, yes.
Okay. And the final, I think, so okay, another question, could you go back to the slides on algorithm and highlight the different architecture used?
You mean this one or this one?
The slides on algorithm.
Yes, here.
Yeah, but
yeah, I think if you mean the architecture of our model, first we modify the attention. Yeah, AGT here. Yes, I think that's this one. First, we have modified the attention and to change the global attention to a local attention mode, adjacent local attention method here. And this is how what we have done to the model architecture. And then we have designed another we have made another modification, change the attention to we call the edge filtering attention, that's using two multi-head attention module, one to learn which to focus and one to learn which to ignore. Here you can see the equation here. The MHA1 learns which to focus. Since it's a minus here, it's minus MHA2. The MHA2 means to learn which to ignore. Yes, that's two different attention mechanisms we have used.
Okay. I think due to the time limit, I think we have the final question. any thoughts on whether the field NCO is heading in other more richer variants of routing? You mentioned some points on the conclusion slide, but it would be great to hear more.
Well, the question is too long.
Any thoughts on
whether
the field, the NCO, the topic is heading in other more richer variants of routing?
Any thoughts on where the NCO is heading in other more richer variants? You mentioned some points on the conclusions, but it would be great to hear more. Okay. So recently I have read a lot of papers about NCO, where NCO may heading, and currently some people using diffusion, some people building a large model and to do distillation for small for specific problems. Some people do multitask, and I think there are if you can find any other related work in other fields for deep learning, and you can use that technique for NCO. That's very easy to transfer the technique to NCO fields. And another is to use the LLM to use the large language model to refine the NCO methods to make a high-level plan of which one to use, like that. And that's also very interesting. And also I have seen some papers in building agents to choose different NCO methods. Yeah.
Okay. I think because of the time limit and we have to stop here. And firstly, I would like to thank Professor Ya-Hui again for his great talk. He presented some recent and very interesting works on the neural combinatorial optimization. And thanks Ya-Hui. And also I would like to thank all the participants for joining this webinar. Thank you very much. Thanks for your questions and also the discussions. Thanks. Finally, I would like to say we have another webinar on 26 May this month about multi-objective optimization, and we will test it very soon. If you are interested, please join the webinar in the future. Thank you. Thanks, Ya-Hui.
Thanks. Thank you all.
So what I wrote, I could probably, yeah, or